This video is on rate influencing factors. So we learned about the collision theory in a previous lesson, and that says that in order for two reactants to react, they must collide, but not any old collision. It must be a collision with favorable orientation and enough energy equal to that activation energy in order to react. And that is called an effective collision. So not every collision is an effective collision, but the more collisions you can have, the more of a chance you have for an effective collision. So I have a list of about 5 rate influencing factors that we're going to talk about here, and according to the collision theory, and explain why they influence the rate according to the collision theory. So what we have going on here, let's see. There we go. All right. So we have the nature of the reactants. So if you have simple reactants, they are going to be able to have more effective collisions than something that is really, really complex, where you maybe have to have 3 things colliding at once in order to react. So having reactants that are easy to react, that's going to increase your reaction rate significantly. If you increase the surface area, and remember we talked about that in solubility, you increase the surface area by smashing up large pieces, and the smaller pieces you have, the more surface area you have. And so the more surface area you have, the more reactant particles are going to be able to collide. They're not going to be trapped on the inside of a reactant chunk. Temperature, if you increase temperature, you've got the reactant particles moving faster. And so they're more likely to collide because they're moving around faster. And they're also more likely to collide with enough energy because, again, they're moving faster. Concentration, if you increase the concentration, it kind of works in the same idea as surface area. So if you have more moles per liter, you're going to have more reactant particles that will collide than if you had a more dilute solution, which has less solute particles. So that would be, I always give this scenario of if I took 2 students in my room, moved all the chairs and blindfolded them and made them run around, I might get a collision. But if I took everyone in my class and blindfolded them all and made them run around, I get way more collisions because there's more stuff to run into. And the last one is a catalyst. We saw that, the effects of a catalyst when we were decomposing hydrogen peroxide. So if you add a catalyst is something that speeds up a reaction. That's what it does. It doesn't enter the reaction. We basically can use it, and then it comes out in the exact same form as a product, and we can take it out and reuse it if we wanted to. Enzymes are biological catalysts. So you learned a lot about those in biology. So we also use enzymes in chemistry as well. But their enzymes are catalysts, and they do speed up a reaction. The opposite of a catalyst is an inhibitor. While most of the time we want to increase the rate of reaction, if we need to slow down a reaction for any reason, we would use an inhibitor to make that reaction happen a little slower. Now, the way catalysts work is that they speed up a reaction by giving it another pathway. They lower the activation energy. So the reaction does not have to collect as much energy in order to break all those old bonds. The catalyst helps it out that way. So what I have next is a energy diagram, and it's actually like 4 different energy diagrams layered on top of one another. I'm going to talk about each of them as we go. So the first one is going to be our uncatalyzed reactions. So just reactants and products here. No catalyst is added in this first one. So we start with our reactants, and we are collecting energy to make up that activation energy. This reaction is going to be so very slow because the activation energy is so high. And then we've made that activated complex, and then woo, we make products. All right, so the making of products happens fast. It's the activation energy that's going to take a long time. And in this one, we had an activation energy of 75. So in the next one, we're going to add a catalyst. This one, for this particular reaction, is going to be a chemical catalyst. Again, we start with the same reactants, but we have added a catalyst in there. And so this reaction is going to happen a little bit faster, but we still have to collect 58 kilojoules of energy to break all those old bonds. Then we have our activated complex, and then woo, products form. All right, so this reaction was a little bit faster because we have an activation energy that is quite a bit lower at 58 kilojoules. This next one is enzyme catalyzed. So for this particular reaction, an enzyme worked out really, really, really well, and would probably be what we would want to use for this reaction as it goes. It's not always an enzyme that's better than a chemical catalyst, but in this particular reaction, it is. So we start with our reactants, we add that enzyme catalyst, and then we have our activated complex already, and boom, we have products. We went from an activation energy of 75 to 4. So that activation energy is way lower. The height of the hill is lower, and so this reaction will happen a whole lot faster. This last one is a energy diagram for a reaction that happens in 3 steps. So we have I'm going to do this one in blue here. So we have our reactants, and they're going to form some intermediates. And then so that we break all those old bonds, and then we have some intermediates. And those intermediates are going to react, and then we get some more intermediates. And then those might react with some leftover reactant, and then we have the products. So you would count the hills in this case. So this reaction happened in 3 different steps. And so you get a hill for each step, breaking those old bonds. Now this last little bit's a little beyond this particular course, but I did want you to know what was going on. And the main purpose of this graph, though, was to show you that a catalyst speeds up a reaction by lowering the activation energy, so it makes that hill smaller.